So I give you the example of the temperature in a room. So it may have a different number at every location in the room. So a scalar functions is a real value function. Okay, so that's kind of the intuitive idea of a scalar field. Now we move on to the vector field. So a vector field, I kid you not, is a field of vector. So it's a field of vectors. We always stay inside a vector field. Right? The airflow is a vector field. Okay. When you go outside, you're affected by wind. In wind, a windy environment is a vector field. So a vector field provides not only the value of something, so bear with me here, at each point, but also the directions in which each value is moving. So again, this kind of the example that I mentioned is that the airflow in this room, at each location can measure the temperature, but also can tell the direction in which the airflow is moving. Vector fields give rise to very important concept in applied mathematics. When I have applied mathematics, you can apply this into physics, biology, and chemistry as well. All right. So the vector field gives rise to two very important concepts. The first one is the curl, and the second one is the divergence. All right. So when you look at this map, you can kind of tell a lot of story about the motions of the movement of the wind and current with the ocean. Okay. So when you look at certain points, right here, that you can see at this point right here on the ocean, right? You can see the current kind of like current rotating around that point, so that it can be described using some mathematical concept called the curl. Right, so the curve tell you describe how an object moves or certain thing moves around certain point on the map. Okay. Now, if you consider some point here, well, this point, ocean. You can see this point, the curve of the vector field move in of this point and out at the same time. Okay. So that's particular motions can be described using the mathematical concept of divergence. Okay. We look more into this two concepts later on in the course, probably after the break. But it's very quite important to understand the curl and the divergence in one another. See, by looking at this, you can actually map out the mathematical formula for this topic. All right, so the curve describes how an object moves around a certain point in space. All right, so the object that I mentioned here, or in the example that you see earlier, is actually the current of the ocean. You can track the motions of the current at certain point in the ocean. And the second concept is the divergence of a vector field. And tell us the net flow of fluid into or out of every point in a plane or in space. Then tell us the net flow of fluid into or out of every point in space. Right. So the curve tell you like so the divergence of the vector field and the curl. The divergence of the vector field is going to be the dot product. You will see that when we get to this lecture. And the curl is the cross product. All right. So in real life, if after to this class, you go to the bathroom, you turn on the faucet. Right. The water running down. That is from the source. The divergence is positive. Now the water will go down to the sink. Right? When it go down to the sink, the divergence is. And now in the okay, so that's good. Now let me move on to a more formal definition for the scalar field and the vector field. So let D be a set in R2, a scalar field in R2 is a function P of X comma Y that assigned that is assigned to each point X comma Y on D. Now in 3 dimensions, in R3, you have the point X, P of X, Y, and Z. is a scalar functions at each point x, y, and z in space. All right, so this function p of x comma y or p of x comma y and z, right, is a scalar function or it's the real value function, just the regular functions that you usually deal with in multivariable calculus. Now for the vector field, let's let D be a set in R2, a vector field in R2 is a vector value functions right, of this form, f of x comma y, right? So for f is the vector value function that is assigned to each point x comma y on D. Right, you can carry the same definitions for the vector value function or the vector field in 3 dimensions as well. But in practice, usually the vector value functions or the vector field can be written as f of x comma y is equal to p of x comma y comma q of x comma y, where p of x comma y and q of x comma y are scalar fields or vector value or the real value functions. Huh?
Says for P, X, Y, and 2XY are scalars. That's a no scalar.
So this the vector field have 2 components to take into 2-dimensional. Now, what I'm going to do next is we're going to look at the line integral of a scalar field. Okay. And I go back to the idea of the integral calculus that we learned in calculus 1, right? The definite integral that is, right? You have the definite integral from a to b of f of x dx, right? And usually in calculus 1, they don't just directly give you the formula that calculate the area of the curve. So what we did is that assume that as is the area of the region bounded by the curve y equal to f of x, two vertical line x equal to a, x equal to b, and also x axis. To do that, to calculate that, they start or to calculate the area of the regions. They start with approximate the area of the regions by putting in a bunch of rectangles. And to increase the accuracy of the approximations, they increase the number of rectangles used in the approximations by increase to infinity. So definite integral is actually equal to the limit of the Riemann sum. Remember that, right? So limit of the summations for I going from 1 to n, and as n go to infinity, of f of x sub I times delta x. So that is actually the formula for definite integral. F times delta x, that is the area of the rectangle. Just add all the area together and increase the accuracy by taking the limit of the term. So this is basically the area of the regions bounded by y equal to f of x equal to a, x equal to b, and the x-axis. So again, the formula we see here is the definite integral. Right, so definite integral of single variable functions are the integrals along x-axis. And it will tell you the area of a flat surface. Or flat surfaces. But what if we don't have the x-axis? We no longer have the x-axis. We now follow a certain curve or certain path, right? So we use something called line integrals. Right? Intuitively, line integrals are integrals of functions along a path or curve that is different from the x-axis. So in general, a line integral gives the ability to integrate multivariable functions or scalar fields or vector fields. Over arbitrary curves. In the plane or in space. you have any questions when you read this statement that the line integral gives the ability to integrate multivariable functions? Have you done that before? Like integrate multivariable functions? Using double integral, triple integral for that matter. So eventually, we're going to learn some concepts, some theorems called the Green's theorem, the Stokes theorem, and divergence theorem. And we're going to relate the line integral toward double integral. So this is a lot easier when you consider line.
Do the double and one and both in one.
But there are certain situations it's easier to use double integral and triple integral, but in general, it's a lot easier to integrate multivariable functions using line integral. Just definite integral. Okay. So this two pictures depict two concepts of line integral along this scalar field and line integral. So in the first picture here, this is the line integral of a scalar field. And it's going to give you the surface area. Now for the second picture, this is line integral inside a vector field, or usually I just say line integral of a vector field. This tell you the work done. Right. The next part of this lecture will be spent on calculating or deriving the formula to calculate the line integral of the scalar field. In the next lecture, we will talk about line integral. What we're going to do next is derive a formula for calculating the line integral of a scalar field. Okay. And before we do that, I just want to go back and mention about the integral calculus, or more specifically, definite integral to calculate the area of the regions bounded by the curve y equal to f of x, the x-axis, and the two vertical lines x equal to a and x equal to b. We're going to do kind of similar approach. That is, instead of directly give out formula, I'm going to start with some approximations. Then to increase the accuracy of the approximations, I'm going to take the limit of the summations, like something like that. So here's what we want to do. So here you have a curve. Consider the curve here. This is in yellow or orange, for that matter. So this is a three-dimensional curve and is written as z equal to f of x comma y. All right. So the job is that I want to calculate the area of the regions bounded by the curve Z. Right. The path in red, I'm going to call that path C. This is capital C. And the two vertical lines are Z equal to, let's say, A and Z equal to B. Okay. So what we want is we want to evaluate the area of the regions bounded by the curve z equal to f of x comma y, the path capital C and two vertical lines z equal to A and z equal to B. So we're gonna do the same approach as when we did the definite integral for a single variable functions. What you do for the surface area, for the area of the region, is that you partition the area or the regions into multiple rectangles. Okay. But now instead of dividing the x-axis into n sub-interval, you're going to divide the path C into n sub arc length. Okay. So this right here, instead of delta S that you see in the integral, definite integral, here I'm gonna call this delta S. So then the area of the regions is approximately equal to so you have A approximately equal to f of x sub I comma y sub I times delta S sub I. Give me a little bit of space here so that we can include summations later. Right, so this product right here, it's just the area of the rectangle of the ith rectangle. Okay? That is delta S is the width and f of x sub I comma y sub I, that is the height of the rectangle. So here I want to note that this one is the area of the ith rectangle. Now you break down into n sub-interval or n rectangles. So therefore, to approximate the area, you take the summations of this product. Right, so for I going from 1 to n. And of course, to increase the accuracy of the approximations, to increase the accuracy so what you do is we increase the number of rectangle to use. Technically, we're going to increase that to infinity. So that is what you do is A is no longer have the approximately equal to sign. We have an equal sign, right? So you take the limit as n go to infinity of the summations for I going from 1 to n of f of x sub I, comma y sub I times delta s sub I. All right. So in practice, nobody wants to do this kind of approach by taking the limit of the summation. It's going to take a lot of time and effort. So what we do when you have the single variable calculus is that when you take the limit of the Riemann sum, you turn that into a definite integral. Okay, we're going to do the same thing for this case. Right? We're going to turn the limit of summations into a definite integral. You with me on that? All right. So instead of limit summations, I'm going to write. So bear with me here. So this is an integral. We not yet put in the limit of integrations. We're gonna put in the function first. So f of x comma y. Now instead of delta s, we're gonna do ds. Right. This now, if you turn this into one single variable calculus, you have f of x. Right. This is dx. So f of x dx, or x going from one point to another point. You with me on that? Okay. So now you have the integrand in two variables, f of x comma y ds, as moving along the curve C. You're okay with that. All right. So instead of a limit of integrations at this point, I'm going to just write capital C. All right. So when you look at this formula, right, this notation, you know that I want to take the line integral of the scalar field, which is just the real value functions, along a path C. You with me? Okay. So this is the line integral of a scalar field f of x comma y. Right. Scalar field, it's just a fancy name, just to say that this is the real value function. It's just a function that we learned before. And it's a lot harder to calculate the area, the surface area, using this formula. So what we do is that we actually need to turn this into a definite integral in terms of the parameter t. Okay. Right, because you have a vector value function, or you have a function, you can turn that into a parametric functions in terms of the parameter t. Right. So that's what you're going to do. So instead of writing the integral in terms of ds, I'm going to turn that into an integral in terms of dt, right, which is the parameter. But the arc length of the path can be expressed in terms of the parameter t All right, so I'm going to use the suffix again. Delta s sub I is equal to square root of x sub I prime of t square plus y sub I prime of t square times delta t sub I. So you see this formula before, if you go back to lecture 6, when we derive the arc length. So this one. Okay, we're gonna take this formula, this equation, substitute back into the limit of limit of decimations. Now everything is in term of t. Then you have that a is equal to the limit as n go to infinity of the summation for I going from 1 to n of f of x sub I comma y sub I. But instead of multiply with delta s sub I have this the square root of x sub I prime t square plus y prime sub I t square times delta t sub I. So you turn this at this point, you turn this into a definite integral. So this is equal to the integral of f of x, f of x comma y times the square root of x prime of t square plus y prime of t square dt. For t is going from A to B. Here, C is a smooth curve and is parameterized as, so C is that of x equal to x sub t, y equal to y sub t, for t is between A and B. Okay, we good? So this is the formula to calculate the line integral of the scale. But here the calculation depends on parameter t. Any questions? Bobby, it looks like you may have some question. Okay, sure.
Following what you did,
Mhm. Okay. Example. Okay. All right, so let's see the line segment from one point to another point. Um, and f of x comma y is x squared plus xy. Compute the line integral of the function. So give me 1 second here. Hope this illustrations could help us understand what we are. All right. So what we are trying to do is try to calculate the line integral of the functions f of x, f of xy equal to x squared plus xy. So the function is in orange. You okay? So x squared plus x times y. You okay with that? All right. Now, usually you calculate the area of the curve, you move along the x-axis only, but in this case, you move along the line segment connecting the point. This is the point here. 1, 2, 2, 2, 5. So this is 1, 2, 1, 2, and then 2, 5. So this is the region. The region include is what we are. You okay? Does that make sense?
Yes, it's not. But
Yes.
why does it not?
Up here.
Yeah.
I think it's at the zoom.
Just like.
The end. So if I zoom. Right, so let me move this to this side. It's hard to see. Here. Better? Yeah, it just. Okay. So that's so the blue region is the one that we're looking at. You good? All right. So that is graphically, that's what we're looking at. But algebraically, how would you do? Now you have to turn everything into parametric function equations for that matter. That means you have to parameterize the line segment connecting the point 1, 2 to 2, 5. All right. And also at the same time, you have to turn, instead of writing x squared plus xy, you have to turn that into something like to t. All right. And everything has to depend on the parameter t. So this is how you do this. So the line segment is parameterized as so bear with me here, C. So the line start at one point and end at the other point. Okay, so start at 1, 2, then 2, 2, 5. To avoid the confusions of the notations, I'm gonna use this notations for vector. Okay. Now you start at 1 point, 1, 2 at the starting point. Good? Okay. You add it with the parameter t, and you multiply with another vector, and this vector is called the directions vector. This is multivariable calculus. Yes, kind of, right. All right, so how we define direction vector? Very simple. You do 2 minus 1 for the first component and 5 minus 2 for the second. Very simple. That's the direction because it's tell you go to that point. Okay. So 2 minus 1 is 1. 5 minus 2 is 3. And this is your parametric equations of the line segment connecting the point 1, 2, and 2, 5. Cool? All right. And what is t in this case? T is between 0 and 1. How can I know this? Now, if t is equal to 0, start at the point 1, 2. Good. When t is equal to 1, then you have 1 plus 1 is 2. 2 plus 3 is 5. You're at the end point. And everything is in between 0 and 1. Cool. All right. So you get 1 comma 2 plus t times 1 comma 3. And again, this is called the directions vector. Here you have t is between 0 and 1. So when t is equal to 0, you add the starting point 1, 2. When t is equal to 1, you add the ending point 2, 5. Now, instead of writing in this form, I'm going to write that in terms of an equation like this. So the curve C can be written as x of t equal to 1 plus t, and y of t is equal to 2 plus 3t. Right, so x of t, just the first component of the vector, that is 1 plus 1t. The second component is 2 plus 3 times t. Just a second. So the curve of the path C is parameterized using this formula. Now for the function, instead of x and y, you substitute x and y by 1. Substitute x by 1 plus t and substitute y by 2 plus 3t. You get the answer. So the line integral of f of x comma y is calculated as, so you have the line integral along the curve C, or the path C, of f of x comma y ds. Right, so this is the general formula to find line integral of the Scalar field. But in practice, we don't use this. We turn everything to parameter t. Right, so you have the line, the integral or the definite integral from, bear with me here, from a to b of x squared plus xy times square root of x prime of t squared plus y prime of t squared dt. So just substitute everything that we know into the formula. We should get the answer. So the integral is from 0 to 1 because everything depends on the parameter t, and t is going from 0 to 1. X now equal to 1 plus t. So you have 1 plus t squared plus x times y, that is 1 plus t, times 2 plus 3t. Multiply with the square root. So x prime is 1. 1 square is 1. So 1 square here. Y prime is 3. So you get 3 square dt. So for this type of problem, I care much more about the setup. As in order to arrive at this answer, it's not a straightforward process. So I care more about this than the calculations. Okay. So therefore, when you do your work out details, you should have something. But again, I care more about the setup. So if you do the calculations correctly, you should get square root of 10 times the integral from 0 to 1 of 4t squared plus 7t plus 3 dt. And this is equal to 5 times square root of 10 over 6. This is unit square because what you get for the line integral of a scalar field is the surface area. Therefore, it's unit square. Right, so this two step right here is less important than steps. All right. Any questions for example 1? Good. Good. Now for example 2, the setups be very similar in it's just that now you have the point in 3. So 0, 6, -1, 4, 1, 5. Gonna do the same thing to parameterize the line segment, connecting these two things together. You start out with 0, 6, -1 plus t times the fractions factor.
That's one segment could be curved.
Mhm.
Would it be different, a different process for it to be a curve with
Yes. So the approach is going to be a little bit different because here you have to manually do the parameterization process. Now, in example 3, you have this is the path, right? So the upper half of the unit circle. Now, what is the parametric equations of the circle? What is x of t equal to? You have seen this before. And I know you know it. For sure, for sure. And when I say the answer, I was like, ah, I know it. What is x equal to? Yes, cosine of t. What is y of t? Sine of t. And that is the unit circle, but you want what? The upper half of the unit circle. Now you take into account the value of t. Okay, so what is t is going to be from 2. Isn't that awesome? Yes. Okay, good. Now, in the homework questions, you have 4 questions, right? In the last question, it's going to be something similar to this, but you already have the curve. The curve is in the parametric form. You don't have to manually. Okay, so let me go back to example 2. And this is what you got for example 2. So here you have So f of t, g of t, and h of t is just the connection of the parametric equations of the line segment linked to 2 points. And the function you have is x squared times that time y. So x squared should be x squared times y. So I did wrong here. So instead of h of t, it should be g of t. That's the typo, but you get, hopefully you get the idea. We good? Okay. Yes.
That's one point. Or two, where the curve is, that's going up, this goes wild, like,
So supposed to calculate something like this. This area.
the area too.
Yeah, to the line, not to the x one. Okay. So for example, you have this point here. Okay. So on this sheet, so one calculates. All right, where were we? Okay, so we need to parameterize the line segment. You're gonna start at the point 0, it's +6, -1. And you do plus t times the directions vector. So the direction vector is, so 4 minus 0, you get 4. 1 minus 6, you get -5. And 5 minus -1, you get +6. So the line segment C is parameterized as so you get C 0, 6, -1 plus t times 4, comma -5, +6, for t is between 0 and 1. Then C can be written as so x of t is equal to 4t, y of t is equal to 6 minus 5t, and z of t is equal to 6, minus 1 plus 6t. Again, 4t is between 0 and 1. Now the line integral of the function is so f of x comma y. Now you have x squared times y, but x is equal to 4t, and y is equal to 6 minus 5t. So you turn this into a definite integral from 0 to 1 of x squared, which is 4t squared, times y, which is 6 minus 5t, times square root of 4 squared plus negative 5 squared plus 6 squared dt. So again, I care about the setup more than the results. But if we do the calculations out in detail, we should have, this is the integral from 0 to 1 of 96t squared minus 80t cubed times square root of 77 dt. And the result is 12 times root 77. And this is unit square. Good. Any questions? Gonna move on to the last example, in example 3. We want to calculate the line integral of the function 2 plus x squared times y ds along the upper half of the unit circle. So we talk about the parametric form of the unit circle. So let me. Okay, so let's write down the detail, a little bit of detail first, and then I will show you the illustrations. Okay, so the upper half of the unit circle is parameterized as x of t equal to cosine of t, and y of t is equal to sine of t, for t is between 0 and pi. So this is the problem that we are dealing with. Good. So again, 1 and 2 is the one that. Any questions? Again, Bobby. This one?
Yeah.
Yes. Because the curve is something weird, right? So kind of the cubic functions here. So 2 plus f of t squared times g of t. So that's why it's a little bit curved. Cool, cool. All right. All right, so the line integral is so this is the integral, right? So the integral of 2 plus x squared y ds. Now you turn everything into parameter t. Everything depends on parameter t. So you have the integral from 0 to pi of 2 plus cosine squared of t times sine of t, and then multiply with x prime, which is negative sine of t squared, plus cosine squared of t dt. Know where all of this coming from? Okay. So this expression is just equal to 1. So we're just going to drop it. Now we just need to do with this 2 plus cosine squared plus sine squared of t. So this is equal to the integral from 0 to pi of 2 dt plus the integral from 0 to pi of cosine squared of t sine of t dt. The first integral, very easy. All right. Now for the second integral, I'm going to use integration by substitution. So things going a little bit time. Yes. Yeah. Give me the answer. So this one is easy. How many of you already registered for integration B? Or if you know about integration B? Okay. You should try it.
See, I just write
Derivative B.
B.
Never thought about it, but that's very interesting. Why is integration B? Now I wonder. Hmm.
I think
You sure about that? Mhm. Okay. Yeah, you should enroll in integration B. Give it a shot and see how it goes. Embarrass yourself a little bit. Why not, right? What? All right, so as I said, the first one is supposed to be easy, yes. So the first one is just 2t, evaluate at 0 and pi. But for the second integral, I'm going to use a different color here. You let u equal to cosine of t.
Therefore, du is equal to negative sine of t dt. Right. Or negative du equal to sine of t dt. Because you changed the variable, now you need to change the limit of integrations as well. So this one is t, this one is u. When t equal to 0, cosine of 0 is 1. When t is equal to pi, cosine of pi is -1. Thank you. So integral now becomes the integral from from +1 to -1 of u square, negative u square du. So the limit of integration is in the reverse order. Apply the negative here, put it back to the correct order. So here you got 2t evaluate at 0 and pi plus the integral from -1 to 1 of u squared du. Or this is 2 pi plus 1/3 u cubed from -1 to 1, or 2 pi plus 1/3 times 1 cube minus -1 cube, or 2 pi plus 2/3 unit square.
Any questions? Bobby?
Oh, no, we just do the integration slightly. You can rewrite it in terms of what you have versus rewriting the.
Is that?
It doesn't make sense.
Yeah, but is that the approach that we use?
Yes. Between high school and that's how that was around. But when I get students who do this too, so I know how it works, this is just.
Okay, good. So one thing some of you know about, I'm not originally from the States, right? I didn't go to high school here. I have a few years of university in my country, Vietnam. So when I come here, there's a lot of technique and terminology that I know the math, I get the answer, but there are so many other things that like, I need to play catch up on. Like at this point, I'm still learning as well. So it's good to know there's another. Okay, so with these 3 examples, hopefully it's give you enough information for you to do the last problem on homework, the written homework. Okay. So when you do that during the break, let me know if you have any questions, okay? All right, so let's cover the last topic here, piecewise smooth curves. So if you have something like this, so the curve consists of 2 pieces, C1 and C2. What you do for the line integral of the scalar cube is that you can break it into multiple integrals. You can do the integral along path C1 first, then add with the integral along C2. So that's what you can do.
if the curve C consists of a finite number of smooth curves at corner points, then we say that C is a piecewise smooth curve. So now when you do the line integral of a scalar field, you can break that down into multiple integrals. So integral along path C1 plus the integral from along the path C2. Then you have the line integral along path Cn.
Cannot visualize this one, but my guess is that when you have a curve like this, so there's a surface area here, surface. Does that make sense?
Sort of.
Um, so for example, you have two regions like this.
Okay.
Okay. And then you can have one. All right, so example 4, find the line integral of this functions x minus 3y squared plus z over two different paths.
So here the line integral is written as the line integral along path C1 plus the line integral along path C2.
So there are two line segments that we need to create here.
So C1, okay, so starting from 0, 0, 0, plus t multiplied with the directions vector, which is in this case 1, 1, 0, for t's between 0 and 1. Now for path C1, x of t is equal to t, y of t is equal to t, and z of t is equal to 0. Now for path C2, well, you start at the point 1, 1, 0 and you end at the point 1, 1, 1. So 1, 1, 0 plus t times the directions vector, which is 0, 0, 1, for t is between 0 and 1.
Yes. For like segment, for like segments between 0 and 1, but for everything else, it's not always 0 and 1. For example, in the last problem, t is between 0 and pi. It just happened the like segment is between 0 and 1.
Then C2 can be written as, so x of t is equal to 1, y of t is equal to 1, and z of t is equal to t.
Good. Makes sense. All right, so I have two integrals. I'm gonna work on the first integral along path C1. So f of x comma y comma z ds is equal to the definite integral from 0 to 1. So the function we got is what? X minus 3y squared plus z. So x is t minus 3y squared is 3t squared plus z, which is 0, so we can ignore that. Multiply with the square root of 1 square plus 1 square plus 0 square dt. So this you should get root 2 times the integral from 0 to 1 of t minus 3t squared dt. And if you do the calculations correctly, you should get this to be negative root 2 over 2. Then for the integral along path C2, so x is equal to 1, y is equal to 1, so you get negative 3 minus 3 plus t squared. Sorry, plus t only, times the square root of 0 square plus 0 square plus 1 square dt. And you should get negative 3/2 as the answer. So in general, in conclusions, you have negative root 2 over 2 minus 3/2.
The parameterization.
Question. Question. So what is the idea of line integral of a scalar field? What are you calculating? When you get the results, what does that tell you? In general, when you calculate the line integral of a scalar field, the what? Surface area. So in the area in general, one is negative. You know about this. So is everything look very similar to a single variable calculus. Not in the negative quantum, but it dip below the x-axis or the y-axis for, or the t-axis for that matter. So the area is always either zero or positive. You with me on that? Always. But in calculus, right, when you do the definite integral and you get a negative number, this is called the sign integral or the sign area. Sorry, the sign area. That means the solution should be square root of 2 plus 3/2. That's the area. But the area is below certain. So therefore, you have a negative value. It's not that you calculated it wrong, just that the region is below certain line. For instance, in calculus 1, when you calculate something like this, the area of this region, right? The area of this region should be equal to a positive number. But when you do the calculations using definite integral, the definite integral is negative because it's below the x-axis. You cool with that? All right. So again, in this case, we did not do anything wrong, just that it's called the sign area. Good. All right. So that's it for me today. That's it for lecture 8. We're gonna start a new lecture after the break. Okay. So at this point, you should have enough information to do the written homework. And please send me the first draft of the literature review by this Sunday. Give me something. See, the more you give me, the better that I can give you some feedback. Okay. Thank you for being here, everyone. Enjoy your break.